Excellent. Well, let me clean this up here. So welcome. I'm really happy to be here to talk to you today about data preparation and graphics. This is a new webinar in our series, so we certainly invite your feedback at the end of this, what you liked and what you would like to have seen more of. So what I want to do first, before we get into any content, I always like to actually jump right to the end and tell you a little bit about resources, since we want to make sure that once you've seen this webcast, if you want to learn more, you know where to go. And our main little landing site for resources is jump.com/learn. So if you haven't visited the Learning Library, certainly go there, and that's what you're looking at on the right. And the nice thing about the Learning Library is you can click through different topic areas. So for instance, data mining, if you're interested in that. And we have sections for each of the different topics that we have guides for and videos for so far. So if you're learning about regression trees, you can watch a video, read a one-page guide, and really learn through these materials on your own. I also want to point out a new resource we have, the JUMP Academic Community, which is a part of the regular JUMP user community. That's actually my second tab here. And so this is great if you're teaching with JUMP or if you're a student learning JUMP. There's rooms for both teachers and learners, and we have a resources center too, where we've aggregated a lot of our learning and teaching resources for your use. So certainly take advantage of these online materials. We want to make sure that you have all the content that you really need to learn and get the most out of JUMP. All right, so with regard to today's webinar, let me tell you what I wanted to cover, and then of course I'll leave time at the end if you have any questions, and we certainly want to get through those. So this webinar is mostly about how you process your data, since data doesn't always come to us in the most clean fashion. There's often issues with outliers, we have to clean our data, we sometimes have data in a format that's not even correct, or we have data in multiple tables that we need to bring together. And so what I'm going to do first is talk about screening our data for these outliers and cleaning up those outliers or mislabeled categories or basic data quality issues. Then I'm going to talk about subsetting and merging data sets. So subsetting is when you want to take that little piece out of a bigger data set, which is sometimes very helpful, especially with very large data. And merging, so really joining and updating, combining tables when you have them in multiple sources. The next section will be about reshaping data. So this is when you actually have data in a format that isn't appropriate for some kind of graphic you want to make or some kind of analysis you need to run. And there's only a limited number of these reshaping tools in JUMP you really need to know, and then you can be pretty expert at moving around agilely between different formats of your same data. So your same data can really be looked at in many different ways, so we'll talk about what those ways are and what tools there are in JUMP to move you between them. So let's start with the first section, screening and cleaning your data. And although it does look on the outset, I just want to point out that most of these are data prep topics. Within each of these sections, we'll be actually forming graphics that will be facilitated on the basis of our cleaning or our merging or our reshaping. So starting with screening and cleaning, let me pull up a sample data set. So I'm going to use the serial data. And in case you don't know where the sample data is in JUMP, go to the Help menu, and it's under Sample Data. So we reference a lot of sample data in most of our other webinars, so hopefully you've seen this before. But once you're in the sample data section, you can actually pull up the serial data set by navigating directly to it. And what I want to do for this data set is just get a brief overview of what columns we have, what we have observed, and I want to give you sort of my inclinations on how I would process data when I first get it. So I work a lot with experimental data, and people give some horrible data sometimes. So the very first thing I do for any brand new data set I ever see is I go to the Analyze menu and I use the distribution platform, which I'm assuming most of you have probably seen before. But if not, let me give you a brief overview. So the distribution platform is all about one variable questions. So by using it here, what I'm really going to seek to understand is what the one variable distributions are, what observations I have in every single column in my data set. And the reason I want to do this is I just need to see what I've observed to make sure there aren't issues with the data set before I actually get to analysis. So before you do any analysis, this is my recommendation to always put every column you have. You'll see I actually left name outside just because I assume that the names will be just fine. But I'm putting every other column in here to see what distribution or what output I have for each of the variables independently. And so in this step, what I would basically do is just look across and make sure that nothing looks out of sorts. We don't have any observations that seem strange. I do notice I have very few hot cereals and a lot of cold cereals, so that's fine. But notice that this gives you some inclination as to what data you have and what you're going to be working with. And in case you haven't seen it, notice that the histograms in the distribution platform, like all data in JUMP, are linked. So if I select a certain manufacturer, we'll see those observations in every other distribution. So this is a handy way of clicking through your data. But for our purposes here, what we should be looking for is anything that looks strange or out of sorts. So first, something caught my attention here. If we look at fat, the average fat for any of our cereals is 1.44 grams per serving. We have a couple cereals that are actually up at 10, so 9 is actually the maximum here. So with regard to screening data, we can do a couple things, and I want to just show you how I would actually work with these data. So if I select this point, notice what happens right away is because of JMP's global selection, when I select a point in any platform, we'll see it in the table. So right away we can see where this observation is, but now we have a couple options for what we can do with it. So I'll just expand this here. So we're looking at univariate data right now, so one variable at a time. Now the first thing that I like to do, and I'm actually going to drag a box around the 3 observations here that are a little bit strange with regard to fat. So I've selected them. I'm going to right click and I'm going to set a marker for just these points. So under row markers here, we can actually say mark these so I can see them in other plots as we move forward. And I want you to see what happens. So when I applied a row marker, it applied them of course in this output, but it also applied them in the data set themselves. So these are now properties of the rows in my data table. And notice when I click on any of the rows, I can right click that row, and that's where the markers are actually settable. We could also set colors and we could do other things for rows, but the markers are a really handy way to do this. Because now when I produce further output later on, we're going to be able to keep track of those observations. So that's one way I would handle those. Let me scroll to the right a little more. So we've already looked at fat, sodium looks okay. Now fiber, we actually have a couple that have a pretty high amount of fiber as well. Now we can see because those points are not the stars, they're not the same cereals. Those are actually different cereals that have high fiber. So let me actually right click those, and I'm not going to do the same thing. I'll do a marker, and let me make a marker that's different. Let me do a black square so we can keep track of those. Now this is one way to handle marking these outliers or looking for them, but I want to show you something else that I like to do. So let me scroll across. So notice we have calories from fat. This is the same outliers that we saw before. And it looks like we're pretty clear. Sorry, I'm scrolling across fast. I hope that's not too bad with the WebEx. But it looks like we're actually pretty okay with the rest of our variables. So let's return to our fiber. And I want you to see another way we can handle working with these points that we don't think are perhaps right or representative of the rest of the sample. So if I right click, we can of course remove them directly from our data set, row hide and exclude. And hopefully you've seen other videos and you've used row hiding and excluding. This will simply remove them from calculations. We don't want to do that yet. We haven't determined that these are bad points, only that they're anomalous with respect to the distributions we're looking at them in. But here's what I like to do sometimes. Name selection in column allows me to make a new column in my data set that identifies these observations by whatever criteria I'm using to identify them. So in this case, fiber. So I'm going to click Name Selection in Column. And notice what it did, high fiber. And I've actually written in this before, so it remembered what I wrote before when I named the selection. And what it's going to do is, if I've selected the points, the 2 I have selected here, it'll give a 1 in a new column and a 0 if the other columns are not selected or other rows are not selected. So let me hit OK, and I want you to see what this does, because this is a really useful feature when you're actually going through your data and selecting observations. Notice now, those ones I had selected, the ones that have the markers, I also have a new column that identifies them. And the benefit here is this works for anything you select. I might want to select just the topmost in complex carbohydrates. I can right-click those now, name selection in column, and I can call this just high carbo. So let me change this. Now 1 and 0, so the ones I have selected will get a 1, and the unselected will get a 0. And what's nice is you can make an arbitrarily large number of these distinctions. This is a nice way to cut up your data into sections. And later on, when you want to look at perhaps differences among carbohydrates, you can actually use this column to reference the high and lows. So that's one way we can actually handle looking at these outliers and at least marking them. Now, another thing is we can exclude, and I'm not going to do that yet because I want to show you a more neat way to look at outliers and to screen for them. But excluding data is really simple as well. So if you just select the observations you want to exclude in a platform output, you can right-click and exclude right away. This will apply it to your data table, so you're not deleting data, you're simply excluding the rows, so that if you ever want to, you can bring those rows back. Okay, so let me close distribution. So this was a look at univariate outlier screening. And by univariate, I simply mean we were looking at individual variables one at a time. But if we're doing analyses that involve multiple variables at once, it might make sense to look at outliers in a more multivariate type way, a way that takes into account where an observation is relative to a centroid, not just a mean. Let me show you what I mean with this. And the platform we're going to use, which maybe you've seen before, but maybe not, is under the multivariate methods section. It's called multivariate. And multivariate is a great platform in general for when you're looking at relationships among many variables at once. And so let me show you what we can do with this. Let's take our quantitative variables. Multivariate requires quantitative variables because it'll be calculating correlations, covariances, partial correlations, partial covariances. So we'll take our numeric columns and put them into Y. We can leave everything else as a default. And when I click OK, I get my correlation matrix and I get my scatterplot matrix. Now you might notice something. The points that I marked before, those points are all still marked in every platform output I get. And so I have the stars here, and you can actually see these were the outliers with respect to fat, and the bricks were the outliers with respect to fiber, I believe it was. So you can already see that the univariate outliers I've marked actually look a little strange in bivariate space. And by that I mean in the relationship between other variables, they actually are kind of outside these center ellipses. Now with our multivariate platform, I'm going to close or minimize the correlation section. I'm actually going to make the scatterplot matrix a little smaller, so I'm going to drag one of these boxes in, just because conserve a little screen real estate here. And what I'm going to bring up is under the topmost red triangle, and there's a section called outlier analysis. And I want to talk about these three different methods. They're actually all related to the Mahalanobis. So the Mahalanobis distance is a type of covariance adjusted outlier detection or screening procedure. Jackknife distances and t-squares are reformulations of a Mahalanobis. And let me pull up the Mahalanobis first, and then we'll talk about jackknifing them. Now if I scroll down, what this produces for us is really neat. This produces a type of chart, a Mahalanobis control chart, where what we have is for each row in the data set, so the first observation here is literally just the first row in my table. So if I scroll up here, if you see me clicking through and focus your attention down on the chart, as I click through rows, we're literally stepping through each row in the table. So that's the x-axis. Now what the y-axis is here is a little bit more complicated, but this is in essence a distance measure of each of these points to the center of data in multivariate space. Now right now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, is that 11 variables? So in 11 dimensions, we're saying how distant is this point to the multivariate mean of 11 dimensions. Now, if you can't imagine that, you're not alone. None of us can. But we can at least do something simple with JMP to get a coarse representation of this. So let me bring up the three-dimensional ellipsoid, and I'll just use three variables here. So in 3 dimensions, you can see what a Mahalanobis distance would do. So in the first 3 dimensions, we have a center in multivariate space, the centroid, and the distance measure is really a measure of how far these points are to that centroid, but scaled in a special way, scaled relative to the relationships among the variables. Because it's more strange for a point to be distant in a dimension sort of orthogonal to the relationship, that is kind of like these points are. They're in a weird place relative to the relationship between protein and fat. And so the Mahalanobis distance is capturing that at once, how far points are from the center, but also whether they're in a strange place relative to what we would expect given the relationships among the variables. And so this is in 3-dimensional space. So a Mahalanobis distance scales to any number of dimensions. So with all of our variables, what we have is a distance measure that we can actually use to detect multivariate outliers. And this control line, so the blue dotted line here, is special. So this is called the upper control limit. This is how distant we should expect points to be given the number of points we have. Certainly the more observations you have, the more likely it would be, just by chance alone, to get a point that's really far from the centroid. So this is actually going to scale or change with the number of observations that you have in your table. Now you'll notice the point that we saw before, this was the highest in fat. So that point is certainly distant by this measure. So not only was it an outlier in univariate space, not only was it strange relative to fat, but it's also strange relative to sort of the mass of data we have. And so that's natural brand oats and honey, in fact. And notice our other outliers we picked out in univariate space, these boxes here, the high in fibers, they're also strange. But we occasionally have points that didn't come out as outliers in univariate space, so this was Wheaties, but were outliers in multivariate space. And that can happen. We can have points that are reasonable with respect to individual distributions, but unreasonable with respect to the sort of relationships among distributions. And I always like to use this example. If you're at a restaurant and you have a bill that's $10, that may not be, strange relative to how much people typically have for bills, and you may tip $10. That's not a strange amount of tip in terms of what people normally tip at that restaurant, but you just tipped 100% of your bill, which would be strange. So neither of those observations, your tip or your bill, would be univariate outliers, but in multivariate space it would be very clear, right? That's an odd amount to tip given how much people typically tip for bills. So a Mahalanobis distance is capturing sort of that kind of idea. What is strange relative to the distributions? Now I want to make a note about this though. So if we're looking at why a point is strange in multivariate space, we need to be careful as to whether we're really calling it an outlier. Does it really count as a point that shouldn't be included in our data? Or is it good data that we should include but need to think about it in a different way? And this is a tricky philosophical question. It's not even a matter of statistics really, but I think I can walk through this a little bit with you using some of the features in JUMP. So let me pull the red triangle for multivariate, and I want to pull up a different kind of plot. And this is a nice way to look at a lot of dimensions of data at once. So if you haven't ever used it, it's called a parallel coordinate plot. And so let me pull up the parallel coordinate plot. Now the parallel coordinate plot, it's not just available in multivariate. In fact, it's actually under your main graph menu. So you may want to form parallel plots for other data on your own. But what it does for us, and I have just the one point selected, that natural bran oats and honey, and what it's doing for me is showing in the 11 dimensions I have, it's showing the height relative to really all the different observations in each variable. So natural bran oats and honey is sort of high on the calorie side. So the first point for each of these lines is how much in calories each different cereal has. It's sort of high in protein as well, and it's really high in fat, but terribly low in sodium. So that's actually good for us. Medium, maybe lowest in fiber. Right, so you can see how you're reading this. You get a profile for each of your cereals. So if I click to another cereal, let's actually click to the lowest really in Mahalanobis distance, so one of these guys that's down at the bottom. So that is, in essence, the most reasonable profile for a cereal to have, is what the Mahalanobis distance is saying. So actually if I select a bunch of the bottom ones, notice they all have that sort of profile. That's the dominant profile of a cereal, to be sort of low in calories, protein, pretty low in fat, higher in sodium, low in fiber, high in sugars, right? So this is the dominant profile among these different variables. And so our natural oats and honey here, that was strange because it's so different from the profile that's dominant in these data. But here's the point I was getting to about whether a point is really an outlier or whether it is an aberrant point that you need to consider as categorically different in some way. That not outlier in the sense that it's bad data, it's just different. And that is with cereals, and I like this example for this reason. There are different sort of kinds of cereal. I don't mean brands of cereal, but sort of classes of cereal. We have the healthy cereals, the Wheaties, then we have the sort of sugary cereals, and then we have sort of the blander, fibery cereals. So we have classes of cereal. So it might be that this point up here, the one that we think is so strange, that just might be a member of a class of cereals, and we need to look at it relative to its class. And so here's what I want to do, and this is actually another platform and a cool way of representing these data. Let me go to Analyze. I'm going to go to Multivariate Methods, and I'm going to use the cluster platform. And what cluster will do for us, cluster seeks to explain homogeneous subsets or defined as homogeneous clusters in our data. And if I pull this up, we don't have to change any of the settings. I'm just going to take those continuous variables I was using right now, so calories all the way down to potassium. I'm going to put those into the Y column, and I'm going to label by name here. So I want the label, so the output, to label the different categories or clusters relative to the names of the cereals. So let me click OK. I want you to see what I get. This is called the Dendogram. So this is representing closeness between the cereals relative to a structure. And so the further up this structure we go, so this whole big set of serials over here is essentially different from this whole big set of serials. And then as you get closer and closer down, let me click on a lowest cluster. Click on ones like this, notice the profiles of Captain Crunch and Twix, are really, really, really close. They're very close in this dendogram, in this tree. Now to make things clearer, I'm actually going to the red triangle and I'm going to color clusters. And what this is going to do is it's going to color the clusters on the basis of the number of clustering levels we have. So this little diamond here, it's basically setting for us a reasonable number of clusters. So it's the elbow of the scree plot. Basically, the scree plot is showing how much remaining variability is there between individuals, so between serials. So if I go all the way down to 76 clusters, that's like saying every serial is a different class of serial. If I go all the way to the right with one cluster, we're saying every serial is the same, which is in essence what our Mahalanobis distance was doing. So if we set some point here, and it was setting it to 8 clusters by default, if we pick some point where there's a reasonable number of different classes of serials, but not so many that we're just, explaining differences on the basis of noise, we get these clusters colored. And I want you to notice something. Let me select one of the clusters. Notice if I do it here, in the coordinate plot, you can see why these are clustered together. They have a similar profile. They're similar serials. They're a similar class of serial. And let me scroll up. And remember, I was trying to show you that this point over here maybe isn't so weird. It may be just weird because it's a member of a class. And if you look, there's actually 3 serials that have profiles that our cluster analysis has picked out. And those were the 3 that we marked as outliers. In fact, they're just 3 serials that sort of have that profile. So nut, oat, and honey, banana nut crunch, and cracklin' oat bran. So they have this sort of profile it's unique relative to what we've observed. But maybe that's because it's a class of cereals that we need to consider. And the other 2 outliers we found, so all bran, extra fiber, and fiber 1. So if I select this whole cluster, notice that those were strange. Sure, they were the top end of fiber, but they're a member of kind of a fiber-heavy class of cereal. And so my point in showing you this is, picking on outliers, this is probably the most finesse of most statistics, is identifying them is easy. What to make of them is a little bit harder. And clustering helps you sometimes in making sense of, whether an observation is part of a class of things that tend to look weird when you look at them one at a time, or if maybe it's just an aberrant point. And oftentimes when you have data quality issues, so something that is so different because somebody typed it in wrong, now that's usually a little easier to spot. But with regard to regular screening of outliers, your biggest concern often is whether you have a point like this, which we've just seen probably is not strange. I wouldn't call it an outlier as if to say it's wrong data. But that is data that has a mean so different in terms of its fat that it'll probably skew results. It'll be influential in your analyses. So removing outliers is sometimes reasonable from sort of an estimation standpoint. And this is where, by saving to your data set, let me actually go back to that, these columns that have 1s and 0s, this makes it easy for you to go back and run an analysis with the outlier and run an analysis without it. So if we wanted to select, let's say, all the high fiber cereals, I've already saved a column, I can right-click that one, select matching. Notice it'll select in my table all the ones I've marked as high in fiber, and now I can exclude, do an analysis, come back and unexclude, and I can run it with and without those outliers. So as far as screening, the univariate and multivariate techniques I would recommend. The multivariate platform, really nice for looking for those multivariate outliers. And univariate, I think this is something to do no matter what data set you're looking at. Always look at the univariate distributions before running any analysis. And that's actually going to lead into really the next thing I want to show you, which is when you're screening for data quality issues, and this comes up perhaps even more often than screening for outliers. Let me pull up a data set, and my tip or my suggestion was always look at distributions before you do anything else. Well, let's do that, and let's see what's going on with this table. So I'm just going to take all the columns. Again, this is always my recommendation. And I'm just going to click histograms only. So I usually do this screening from a visual inspection standpoint, so I don't really need statistics right now. Let me click OK. Let's look at what we have. So bill amount looks just fine. Here's actually my method. I like to minimize each of these as I go through them. Tip amount, that looks just fine. Credit card, so this looks problematic. We have some people who typed in a yes, some that typed in a Y, some that typed in a no, and some that typed in an N. So that's bad. Number of guests, let's minimize that. It looks fine. Day of week, this definitely looks like we have a problem here. So Wednesday, wed, Tuesday, Thursday, different capitalizations. Some of these have spaces in them too. All right, so this would be really bad for our analyses. Same with this one, servers. People typed them in all different ways. Tip percentage looks okay. Now you'll notice when I clicked off histograms, or I clicked histograms only, it also took away my box plots that showed me those outliers. So if you ever want to get those back while not showing the rest of the statistics, remember you can always go to the red triangle and turn on the outlier box plot. And I mention it here because tip percentage is one in which we actually do have some individuals who are tipping a crazy amount here. So those might be things we'd want to look into. But right now, I want to tackle this issue with you. How are we going to clean up these categories? Because when I used to use Excel a lot or SPSS a lot, I would just go and find and replace. That's how I would actually clean up those. But with JMP, there's a much quicker way, and a way I think you'll appreciate the more you use it, because it really cuts a lot of the pain out of cleaning up these categories. So let's start with credit card. So it's clear that credit card was entered in by, it must have been different people, because we have some N's and we have some no's and Y's and we have some yeses. So we could go through and manually change them, but here's what I would suggest. Under the columns menu, you have an option called Recode. And Recode is a really neat idea. Recode takes whatever was previously entered in the column, and what it's going to do when I launch this is it'll accumulate whatever levels appear in this column. And Recode shows me the old value and just gives me a section to type in the new value. And so this is as simple as me saying, well, these N's and Y's should really be no's and yeses. And notice the identity here. It even tells me how many of the Y and the yes categories I have, and how many of the N and no categories I have. Actually, N and Y was predominant in this data set, but I'm actually going to change those. I like the no's and yeses. Why not? So let me click OK, and I want you to see what Recode will do. Is immediately in the table, it'll go through and actually change each of those to be what my new recoded values are. So, huge time saver here. Let's try this for day of week, and I want to show you what I would actually recommend. So you notice that when I recoded, it recoded this variable right in place. And what I like to do, just for a data security issue, I like to recode into a new column. I always like to retain whatever the original data I got was, because if anything ever goes wrong down the line, I want to know what my original data looked like. And so of course save copies of your data set, but I like to do it even within a data set. So here's what I would do. Under columns, let's go back to Recode. And now we're going to handle this Friday, these issues. We have spaces, we have different capitalization. Let me show you a quick trick here. So under the red triangle, I'm going to do the first thing, trim white space. That'll remove all those extra spaces and trailing spaces on the other side that people have entered. So that's just a great thing to do first. So notice that my new values here, it cleared out all of those. And we also have some capitalization issues, Thursday, to Wednesday. I can fix those manually, but I can also just say convert to title case. So every single one of these will now be converted to title case. Now finally, we have some that are spelled out all the way and some that are just spelled out with an abbreviation. Wednesday is the only one, so I'll just change that to wed. So there, that's all the recoding I need to do to fix all of those issues. But I want you to see that I don't have to do it in place. I have the option to do this as a new column, a formula column, or to write a script. Now let me do new column, and then we'll actually tackle the server, and we'll do that with a formula column. So with new column, I want you to see what this is going to do. When I click OK, JMP didn't recode my original column. Instead, it created a new column. And so this new column, let me take them both and I'll go to distribution. So this new column, notice, it actually recoded the values like I specified. And if I click through, you can see where the original categories were and what they are now. And so Wednesday, it took all three of these, and just like I specified. Now, I want you to see something. If I double click in the cells here, these are actual values that have been written to the table. There's no formula, there's nothing happening here. These are just plain old values. Let me go back to day of week. And actually, let me do it with server here. I'll do it with a new column. I want to show you the formula version of this, because sometimes when you get new data in, you want your recoding to continue to work. That is, if you were to enter in new data at the bottom, if I do this here, let me put in a lowercase Monday, notice at the bottom, this new column, the recoding column that I made just before, it doesn't know how to do anything. It can't recode that for me because I haven't told it what to do with it. But we can actually write a formula column from Recode, which will dynamically recode every time you enter new values. And this is really neat. So let me go to columns again. Let me go to Recode. And this one again, we have some crazy issues. I'm going to do these quickly. So I'll say convert to title case. Let me actually take out server for each of these. Somebody typed in servers as well. So we just have B, 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 C. Right? And so that's actually all we have to do. But instead of doing in place, instead of doing a new column, I'm going to do a formula column. And what formula column will do, it'll make a new column, of course, and it will look like it's writing the values. You can, of course, double click, you can click on them. But I want you to see that the way it's doing this is dynamic, because watch what happens here. I'm going to put a lowercase a for server, and watch what happens over here. It'll recode it. Let me put in server a. If I do that, it recodes it. It knows the categories that I recoded. It's using a formula to accomplish this. And the way it's doing it, if you right-click and go to formula, what this conditional function is doing is just a match. It says, look at the server column, the original one, and if it's any of the things on the left, make it the thing on the right. And so what it's doing is any of the categories I recoded before that are a part now of the match function. Of course, anything it doesn't recognize, it'll just put a server. That is, it'll actually just write down whatever the value you put in that column is. So for instance, if I put in server D, it doesn't know what to do with server D, so it just puts it in as server D. But I'll show you something neat. So if you have people entering in data all the time, and you don't want this column to ever get polluted with values that don't make sense, you can actually just take out server D and put in quote, quote. So a blank. And now, if people, oops, it actually won't work, I forgot. If we do this, it will get rid of the categories that were right to begin with. So I forgot, we have to expand this function out. But there is a way you can write this in such a way where if people enter in wrong values, maybe just do this through value check or list checking, then you won't have a new column polluted. So especially when you're automating data analysis, this gets to be a useful thing to do. So I'll edit that in the video I post actually, and I'll show you how to do that. I know we're running a little bit close on time here. But so the automatic recoding with formula is really neat. And again, because if you keep adding data in and they're categories you've seen before, then it'll actually recode for you. All right, so that is the screening there. All right, so what I want to show you now, so assuming that we have data we've cleaned, data we've screened, we're comfortable with the outliers, what if we actually have a situation with like a restaurant tip? So this is the clean version of that. But we want to break out our data set into separate server sections. So right now we have data sets that are combined. We have server A, B, and C all in the same table. So there are times you really want to consider just a subset of your data, but you don't want to do it through a data filter. So remember, under the rows menu, your data filter will always let you filter or select a subsection. So I can click on server, and I can tell it that I only want to use server A, B, or C in an analysis. So if I click include, what this platform does, the row filter, is it will actually just select and include only the ones that I'm selecting. So if we didn't want to do that, if we really wanted a totally separate table for our analyses, here's what you can do. Let me actually clear the row states, so get rid of the exclusions. But I want to point you to the subset tables function. Because what subset will do is this exact idea. It'll take a piece of your data set out. And this is really neat. So you can do this in a number of ways. So first, with regard to which rows you take out of your data set, you can have it be all the rows you've purposefully selected. So if I go back to my table and I select just a few of these, subset will actually bring out just those selected rows if I want. Or you can have it do a random selection. So this is great when you're actually working with really large data. So I have a couple that have 10 or 15 million rows, but I just want to pull out a random sample of 100 and work with those for some reason. So you can actually randomly sample from your own bigger data sets or even stratify from your actual data set. Now I'm going to leave all rows on, and under columns, notice we also have the option of selecting which columns to take with us. And this is actually really neat. So sometimes you actually want to, especially when you're working with really massive data sets, you only want to take a few of your columns, so bill amount and tip amounts. So you don't care about credit cards or number of guests or anything like that. You just want 2 specific columns. So you can select selected columns and JMP will only take those. Now, I prompted this whole thing by saying, what if I wanted separate data tables with just the server? So just server A in a data table, just server B in a data table, and just server C in a data table. So here's how I would do that. Let me turn on all columns, and I'm going to click the button subset by. And subset by looks to a variable. So I'll give it server here. And what it looks for is different levels in that variable, and it'll make you a separate data set with the observations occupying the different levels. So if I click OK, we get 3 tables, as we should expect. We have 3 servers. And these are just the observations for server C, for server B, and server A. And so a really handy way of breaking out that data if you really need to. Now again, I don't always recommend that. I think I would rather use a row filter if I could. But maybe from here on out, you really have to maintain separate tables. So you want to break those apart. And so that's what subset can do for us. Now if you want to bring them all back together, there's actually sort of the inverse of this. So under tables, there's the option to concatenate. And concatenation of a table is taking tables that have the same columns, but squishing the rows together. So in this case, we have tables that have the identical columns because we just subsetted them, but they have different rows. So if I go to tables concatenate, we simply have to add in to the section on the right which tables we want to be squished together or concatenated together. So A, B, and C. Here's what I'll just mention what I like to do. If I click, I'll click Keep Dialog Open, and I'll show you this will work just fine here. It'll actually squish the table together. It even adds back in the server column, so server A, B, and C for us. So actually, this is our original table. But I'll show you what I want to do. And this is just me suggesting something from my own experience working with concatenations. I always check create a source column. And the reason I do this is even though I do retain the server column that I originally had, that definitely comes back in, I want this source column, and I'll show you what this looks like. It's an extra column that gets added in that says, what was the name of the table that this came from? And the reason I like that is, especially when you're working with complicated data sets where you have tables from lots of different sources, I just like that written to my data set. I mean, data is cheap, and having, or space I should say, in your computer is cheap, and having one extra column that could save you a headache down the line is completely worth it. So I would recommend checking create a source column, just save yourself the time down the line in case something goes wrong. Not with the concatenation, but just with regard to finding where the data came from. So that's what I would do there. So subset and concatenate sort of work in those opposite ways, breaking out your data set into pieces and squishing them back together if you've worked on those pieces. Now I'll mention something with subset, and this is really cool. You know, sometimes you have a selection of rows. Let's say you just want to look at server B. So I'll select just server B's. Now you can actually create a subset just by right-clicking on the selected. So I'll just do data view. And what data view is, this is a little linked subset. And so a linked subset is a subset of the data where these rows, even though they're in a separate table, these are linked to the original table. Notice when I'm selecting them in here, it selects in the original table. If I change an observation here, it'll change in the original table. If I make this observation 10, notice it just updated in the table. So what's neat about this is sometimes you need to work with a little tiny piece of your data, but it's overwhelming to look at your whole data set. And so this linked table, a linked data set, works like that. You can select any rows you want, and under selected, you can just right-click and do data view. Now alternatively, you can do this formally under the subset platform. So under tables subset, like we just did, there's actually a checkbox for link to original data table. And that's what's called the linked subset. So if I do a linked subset here with just, let's say, these 5 rows, and let's say I only care about these 2 columns. Remember I was mentioning that before. Maybe I just want to work with that piece. So if I have selected rows and selected columns, and I click link to original table, this will make me this tiny linked subset. And these observations, if I change them, maybe these are data I'm cleaning up and I only need to consider these. If I change these observations, they'll change in the original table. These rows and columns are literally these rows and columns. It's just a aliased data set that lets you kind of think more clearly if you have a ton of data. And so I like to do this when I have very, very wide data. So with tens of thousands of columns, I just simply can't work with a data set that big sometimes. I like to have the small linked data set that I can work with. Now this doesn't get saved separately. It's actually not even a separate table. It's just a little trick that JMP is doing to help you see or to focus your attention. So that's something I would recommend. Again, you can do that under subset by clicking linked, or you can right click on the selected and do data view. You could also do this when you double click a histogram. So you can basically invoke the data view from lots of different ways. So I'd recommend that. Okay, so that's subsetting and merging when we're just working with rows, but imagine we have a situation like this. We have a big data set. This is US demographics, and this data set is actually pulled from lots of different sources, from different census data. So we have states, but clearly there was no one who had a data set that had, population, 8th grade math, but also vegetable consumption and smokers, right? As well as alcohol consumption and college degrees, right? This data set was made by squishing together lots of data sets. So let's see how we can do this. Let me actually bring up individual tables. So here are some of the attributes we had. So states and gross state product, vegetable consumption. We had some basic demographics. So this had the IQ, the region. We had educational characteristics, right? So 8th grade math, high school graduates, college degrees. And we finally had one with just household income. So that was an income data set we found. All right, so how could we get these all together? Well, with 50 rows, and since we can be pretty sure we don't have redundant or missing states, because we have 50 rows in each, yes, we could just simply copy and paste these together. That would actually be fine. But let's imagine, just for the sake of us doing this, but without bringing up a really big data set, that we have tens of thousands of states in some way. This is maybe counties, or this is regions in the world, or something like that. So a situation where we really wouldn't want to do this manually, and I'm sure you've all had data sets where you really wouldn't want to do something like that manually. So here's what I would do. Under the tables menu, there's the option of using join and using update. Now let me show you update first. Update is a real simple and sort of simple-minded procedure. Join can get a little hairy, so let me show you update first. And what update does is merge columns, in essence, between two tables. But it's going to do it for you on the basis of a matching criterion. And this is what makes it so neat, is our tables, notice, every one of these tables, they have states. So every one of our tables has something that relates the observations, even though we don't have the same columns. Alabama here is the same unit of analysis as Alabama here. And so we would call this a key. It's a key that matches the rows that should go together. And so in the update section, so again under tables update, when we're using update, we have to first tell JMP we want to merge the basics data set with something else. Let's do it with attributes. So that was this data set that I have already here. And we're going to tell it that we want to match columns. And match columns says what columns in this first data set in basics matches with the column in attributes. What gives you the identity between these that you would be paying attention to if you were to squish these data sets together? And for us, that's going to be state. So I'll click state under basics and state under attributes. I'll click match, and I'm basically done. Now I'm going to click keep dialog open because without changing anything else, I want you to see what happens. When I click create, JMP is actually going to append to my original data set those attribute columns. And look what it did. It just stuck the columns at the end. I've built out a bigger table. And so I can do this now with all of my data sets. So instead of doing it with attributes, let me do education. So I'll do state, match, and click create. It's squished now education at the end, college degrees, high school graduates, 8th grade math. We're almost done. Let me do it with income. So state matches with state, match, and click create. And now we have household income. So I've just merged together these data sets. Yes, there was only 50 rows here, but if I had 10,000 rows or 10 million rows, it wouldn't have mattered. If we have a matching variable like a state in each of these, we can squish these together, and now we have our table. We have our table with all the different pieces. Now I use update for that. And update was nice because as long as I have two tables open, it lets me invoke it. What update will do is just bring in the new columns, but it will do one more thing. If two columns have the same name in both data tables, Let me bring back up the original ones here. So if I had, here's my original basics, if I had vegetable consumption in this table, so let's say this was called vegetable consumption, and I used an update, and this table also has a column named vegetable consumption. Now, this is actually a really important point. It will use the new data that I'm updating to, or updating from, to overwrite the original. Now this is both really great and really horrible. So just be aware of this. If you have columns that match in terms of their name, so other than state, if you have columns that match, the new table that you provide is considered to be the better data. It's considered to be the data you're updating from. Now, often this is exactly what we want. If we have two columns with the same names, we mean for us to update from the new data. But if you're not aware of this, then you can sometimes write over existing data. So just be very, very aware of this. If you use tables update, you're telling JMP you want to update. So it'll add any new data it hasn't seen, so any new columns, and it will update any existing data. So if you have columns that match in their name, it'll assume that you're telling it to update. Now join, on the other hand, lets you work with some other options. We don't have as much time to get into this today. This is a little more advanced of a joining, but it does give you options. So if we're joining attributes with basics, just like we did before, we will specify what kind of matching criterion we have. So we select in each table what we're matching on. But here's where it gets a little more complicated. You have your decisions to make about how you do your join. You have an inner join, an outer join, a left outer join, a right outer join. There's actually a lot of different ways we can join tables. And these refer to what you do with multiples, so observations that are in both tables, and what you do with non-matches, observations that are in one table but not the other. So if we have Ohio in one table but not the other, do we include it? And if it's in the main table, do we include it? Or do we include it if it's in the table we're joining with? So depending on how you select these, JMP will do different things with which columns it retains and which rows it retains and which ones it doesn't. This also gives you the option of merging save name columns. So by default, that's not checked. If you click that, that is you telling JMP that you do want to do that updating. So just like the update platform will do that automatically, join lets you turn that on and off. And so I would definitely suggest playing around with this with some practice data. So it will work very similar to how update works, but depending on which selections you make, it'll do exactly as it says, whether it drops multiples or includes non-matches. All right, so let's actually not use that here because what we have already is the table where we did squish these all together. So I want to show you a couple things we can do now that we have this big table again, and this is with regard to displaying these data. And so let me actually pull up Graph Builder. And hopefully most of you have seen Graph Builder before. Drag and drop graphing platform in JMP. And there's some great things we can do with it. And since we have state in this data set, I want to show you one of the things I like most about this. So let me take state, and I'm going to drag it into map shape. And the map shape section will bring up a map of the United States. It knows these are states, and it has the shape files for these states. Now what's really neat is we have a lot of attributes in this data set that are kind of interesting. So we can take something like smokers. Let me drag smokers into the center. And notice what JMP does is it now adds a color role for smokers. So now we're actually seeing in a heat map across the country the different smokers. So we can see California's pretty low, Utah's very low, we have some states that are higher. We can substitute out other variables, alcohol consumptions for instance. Let me drag that over here and drop it on top of that. Let me deny this update. So I just dragged alcohol consumption right on top of color. And notice that we can replace variables like this. So 8th grade math, I could do the same thing, drag it right on top of color and let go. So we can replace variables, but with a data set like this, and this kind of goes with regard to visualization and how we can best convey the meaning of things, it's kind of frustrating and slow for me to keep substituting variables out. So I want to show you a neat trick that's in Graph Builder. So let me click Done. So we have our data set up or our visual set up the way we'd like. Let me go to the red triangle, and under Script, I'm going to go to the Column Switcher. And Column Switcher is neat. This is available in most platforms. What Column Switcher will do is bring you a new control panel that'll allow you to switch out a column that you're currently using. So I'm currently using 8th grade math as my way of doing the heat map. So let me tell JMP that I want to switch that out with other variables. And what I'm going to do is select all these attributes from vegetable consumption all the way down to household income. And so what I'm going to do when I click OK is get a control panel. That jump now lets me click between the different variables, literally a switcher of columns. And so I can click through, and this is a much better way to convey sort of all the different data here, because we can click through, and sometimes, if we want, we can just hit play and let it do it for us. And so this is now playing on a little loop. And this is a great way, especially when you have large amounts of data and you just need to spot a pattern. You know, maybe there's one of these that's going to pop out to you in a particular way where you say, hey, wait a minute, you know, that's interesting. There's something right here that caught my attention. And so the column switcher is a great way to do this. But what if you wanted to show two of these at once? So maybe you want to show smoking and alcohol consumption at the same time, right? That seems a little strange that you'd have to look at them separately. Or maybe it's something even more crazy. So how about alcohol consumption, or sorry, smokers and vegetable consumption? You know, do those relate to each other? And you really want to show both of these maps side by side. Now you can make two separate graph builders, but let me show you a neat way to work with this problem. And that brings us to really our next section. Our last section here is reshaping. And I want to show you probably one of the most indispensable reshaping tools, in my opinion, which is stacking your data. So stacking is the idea, and let me show you really briefly with another data set. Stacking is the idea often of taking observations that are over time or over conditions that are currently across columns and putting them across rows. So in this data set, we have observations for these dogs in 4 different time points. What if we wanted those 4 time points to not be represented across columns, but instead we wanted for each dog to have 4 rows that had time point 1, 2, 3, and 4? And so let me show you this quickly. It's under tables and it's under stack. And the way stack works is you just tell jump which columns you want to convert to rows. So I'll take histamine 0 through 5. I'll click that into stack columns. And what I'm going to do is actually click select here because I want to tell jump exactly what other columns I want to keep. Because if I did nothing else, jump would actually keep all my columns, but I just want to keep a couple of these. So I'll just say drug, ID, and DEP1. And this is just for clarity right now, so you can see what this will do. Now, like I've done before, I'm going to click Keep Dialog Open, so we can come back to this in a second. But just look what jump does when I stack those columns. So it's taken histamine 0, 1, 3, and 5. Those were previously columns, and now they're rows. So these 4 rows are the first subject here. So first 4 rows are the first 4 columns. And so this is kind of reorienting your data now. So we're stacking across rows instead of across values across columns. Now notice that we have a column labeled label that corresponds to right here. That's actually what we want to call the sort of the attribute that identifies what those columns were. Now for us, that was actually time point. And data is corresponding to what we had typed in here. That's what you actually measured, and so that's histamine levels. Notice why each of these account for those things. So the time point is going to be the column that identifies what columns we had, and that's sort of like what factor did those represent. And then this other one is what are we actually measuring. So if I create this table, notice I get columns that are labeled a little more reasonably. So that's stacking. Stacking is indispensable. And notice for this case, you would have to do this if you wanted to model these as a mixed model. Mixed models require your data to be in what's known as tall format. But for us, let me go back, and this is sort of bringing us back to our graphing question. Stacking is what's going to allow us to do this, to make these side-by-side plots, because I want you to see how we can use it here. So I'm going to go to stack, and just to reiterate, what I wanted to do is have vegetable consumption and smokers shown next to each other with 2 separate maps, but in the same output. And so I'm going to tell jump that I wanted to stack these 2. So stack vegetable consumption and stack smokers. And like I did before, I'm going to click the select button because I want to keep only the ones I select. I only want to keep state in addition to vegetable consumption and smokers. And so the data column, this is what data is in these columns. This is really, I think, percent of the population of each state. And then the label is, I guess, which attribute we're talking about here. So is it vegetable consumption or is it smoking? And so let me click OK. And notice what we get now is a table. It's 100 rows long because we have 2 rows for each state, one for vegetable consumption and one for smoking. And we have the columns labeled the way that we wanted, which attribute we're looking at and what percentage of the country or state that's in. Now look how we can use this, and this is cool. Let me go back to Graph Builder. Let's take state. That is our map shape, so drop it there. I'm going to drag percent into the center. Now, think about what this is. This is the average of smoking and vegetable consumption. That's a preposterous thing to look at, but we take attribute now. We can use this in another role. Let's take attribute and do it group for X. And notice now we get our side-by-side plot. So we get two maps, one showing smokers and one showing vegetable consumption. And that, I think, tells a better story than us clicking back and forth through it. Right? We can actually see that these are potentially maybe mirroring themselves a little bit. So something that is maybe tending to be associated with healthy living and one that isn't, or I have those backwards. Smoking tends to be associated with not with healthy living and vegetable consumption with it. But so being able to use this role, using the group for X, notice that we had to have our data stacked because we needed literally a nominal variable, something that was categorical, that identified which of these attributes we were talking about. And so that's what we gained by actually doing it this way with the stacking. Okay, so let me pause there. Walter, do we have any questions?